Hello, my name is Ricardo Cebada. I'm a PhD student at the National Autonomous University of Mexico, and I'm going to introduce this research, which is titled Optimized Performance Pulse Oximeter based on the MAX30102 commercial sensor. Photoplethysmography is an optical technique commonly used in pulse oximetry. Basically, it consists in applying light at different wavelengths, typically red and infrared, in an area of the body irrigated with arterial blood, such as the fingertips. And by analyzing the attenuated light due to absorption, we can estimate the amount of oxygen in blood and the heart rate. By detecting the resulting attenuated light, we get what is called a PPG signal, which comprises a pulsatile and a constant component referred as AC and DC respectively. To quantify the amount of oxygen, the most widely used parameter is oxygen saturation, also called SpO2, which is a measure of the oxygenated hemoglobin relative to the total hemoglobin. In practice, SpO2 is calculated through a linear approximation of the Lambert-Beer law using the equation 1, where R is the ratio of red to infrared components. On the other hand, heart rate is given by the PPG signal frequency, which can be obtained by means of Peaks counter algorithms or a frequency decomposition using the fast Fourier transform. MAX30102 is a sensor for reflective photoplethysmography, mainly using wearable devices whose performance can be affected by factors such as low blood perfusion or movement. So the objective of this research is to propose an optimized oximeter based on this sensor. Regarding the methodology, we first determine an optimal configuration for the sensor parameters of LED current and sample rate to get the best quality signals. Then we design SpO2 and heart rate calculation algorithms adapted to these signals and compare the performance of two heart rate calculation algorithms, one based on a Peaks counter and the other on the fast Fourier transform. At this point, we already had the first prototype, which was evaluated with a series of preliminary tests performed on a volunteer by comparing the prototype with a high-end commercial oximeter. Finally, we carried out a pilot study on a group of 15 healthy people to evaluate the performance of the prototype in a real environment. The results were the following. The prototype was implemented using the ESP32 microcontroller, as you can see in the picture. We found that the optimal configuration for the sensor is to set the LED current to 50 milliamperes and the sample rate to 200 samples per second. The FFT proved to be more accurate than Peaks counter algorithms in the presence of noisy signals. However, there are some limitations to implement it in a microcontroller due to the lack of RAM memory. The preliminary tests pointed out an accuracy of 1.39% for oxygen saturation and 2.04 beats per minute for heart rate. Finally, by means of a blind element analysis of the pilot test results, we found that the measurements of the prototype are within the concordance limits. We have named our prototype Oxipuma, and in the following videos you can see how it is compared with a high-end and a typical low-cost oximeter. It is worth mentioning that in the presence of an optical barrier, such as in the case of painted nails, Oxipuma outperforms low-cost oximeters because its principle of operation is based on light reflection instead of transmission. So, in conclusion, the prototype meets the requirements established by the Pan American Health Organization for pulse oximeters. The FFT outperforms the Peaks counter algorithms for noisy PPG signals. And finally, the prototype measurements are comparable to those of a high-end commercial oximeter. However, further research must be done. Thank you all for your attention, and if you have any comments or questions, this is my contact information.